All right, we'll get started here. Thank you everyone for coming again. Today, it's my pleasure to introduce a visiting lecturer, Dr. Charlotte Apps. She's working with Sandro and Benno Nig for the next year. You arrived in August, I guess. Right. So she'll be here until August 2024. She joins us. She's a lecturer at Nottingham Trent University in the United Kingdom, where she studies the interaction between shoes, individuals, and the performance, benefits of different footwear interventions. And that's what she'll be talking to us about today. Charlotte lived on and off and completed her education in Liverpool with a Bachelor of Science in Anatomy and Human Biology from the University of Liverpool. And then she completed a master's and her PhD at Liverpool John Moores University, where she studied the biomechanical and neuromuscular adaptations to shoe surface instability. She's continued this work so far and has completed some industry-related projects with Li Ning. If you don't know, one of the corporate works or companies that Biomechanic currently works with. And then she's also worked on a footwear project funded by New Balance in 2016. So overall, in general, she's interested in this kind of shoe-person interaction, how we can improve performance. She came to the university here to learn multivariate analysis, such as principal component analysis, and also to collaborate and to start collaborations with individuals over here. Outside of her work, she's an avid cyclist, and she cycled across the United Kingdom in 2021 in 2 weeks, which is 1,000 miles. The bike came with her all the way from England to Calgary, and you can see her riding around the city. So I'll turn it over to Charlotte now, who's going to talk to us about the effect of in-shoe friction on change of direction performance in team sports players.
Thank you very much. It's a real pleasure to talk to you this afternoon on this topic. I find this really interesting because before I got into cycling and running, I actually really enjoyed playing football, or soccer as you call it here. I ended up playing for a team at a reasonable standard called Liverpool Feds in the Women's Northern Premier League. And in soccer or football, there are lots of changes of direction. They're very frequent across team sports. A change of direction involves a rapid whole body deceleration followed by an acceleration in a new movement direction. And the ability of players to do this faster leads to better match outcomes. So it's important to understand how players can change direction faster. A mechanical determinant of change of direction performance is the coefficient of friction. Players can increase this by increasing the relative horizontal forces they apply to the ground relative to the vertical. Research has shown that footwear that provides mechanical coefficient of friction values between 0.7 and 0.8 do increase change of direction performance. So in terms of work that's been done in this area, these are the number of studies here are the ones that I know of, so there may likely be more, but you can see most research has predominantly looked at cleats and outsoles. So this is looking at the interaction between the shoe and the floor. There's been 4 studies I know of that has looked at the shoe upper and how this helps change of direction. But there's been a lot less interest in the interaction between the foot and the shoe and the interface here and how this might help. Recently, Raina Crawford from Darren's group won the prestigious Nike Award looking at a very related topic. I think she presented here looking at a lateral wedge insult on performance. But to my knowledge, there's been really little work done on how in-shoe friction might benefit change of direction performance. So with that in mind, I've got two goals of my talk today. The first one is to discuss 2 studies that I did that assessed friction at the shoe surface. That should say foot-shoe interface And the second goal is to compare the effects of the different footwear design features and how much they can benefit change of direction performance. So the aim of the first study was to evaluate if an insole with higher frictional properties can reduce in-shoe sliding and enhance change of direction performance. For this, we assessed two different insole conditions, a standard insole, which had a regular cloth top cover, and a prototype training insole that was developed with a textured surface and was made of a tacking material. Participants were blinded to which insole condition they wore during this study. The shoe they wore was a prototype shoe that was specifically designed to limit the support of the other shoe components on preventing movement of the foot on top of the shoe. So it had a very stretchy upper, it had minimal wrap of the midsole onto the upper, and it had no midsole. The tightness of laces has been shown to help with foot stability. So we controlled this for participant between insole conditions as well. Mechanical testing confirmed that the training insole, as expected, did increase the coefficient of friction. This was tested using the setup shown here, where a 3 kilo mass was placed on top of some foam that was surrounded with a cotton sock material. It was then pulled at a set speed, and the horizontal forces were computed. The static coefficient of friction is calculated using the peak force just before the sled starts moving, and the dynamic coefficient of friction is the average force during the moving phase. For the biomechanical protocol, we tested 15 recreational team sports players. They did 2 change of direction tasks, a 180-degree turn and a 20-degree cut, which I'll talk a bit more about in a moment. But all participants did 5 trials in each task, and the order was mixed between participants. During the change of direction step, the participants landed on a force plate, so we could get the ground reaction forces to compute the coefficient of friction. And you can see we had a 3D motion capture system to track the movement of the foot inside the shoe. You can see the cameras were really close around the force plate. That was on purpose. And we were really strict with the calibration procedure here, in that the residuals or the errors of each camera, the maximum we accepted was 0.3 millimeters. And this was because we were interested in very small movements in the shoe. So for the 180-degree turn, it looks something like this, with participants starting behind some timing gates. They then ran with maximum effort, planting their dominant foot on the force plate, and then turned and went as quickly as they could back through the starting timing gates. The starting point for the 20-degree side cut was the same, except this time when they landed on the force plate, they then did a cut of 20 degrees towards their non-dominant leg that was marked out with some cones 1 meter away, and then the end point was 1 meter further along. That was, they heard when to stop from the beep of the timing gates. So to analyze the coefficient of friction, we needed to determine what phases to look at. What we're looking at here is an individual trial of one participant during a 180-degree turn task. Typically, what previous work has done to analyze this is they mark the start and end time points based on a 10 Newton threshold of the vertical ground reaction force. However, I found when this was used, the start point included some of this very high signal at the start and end of the coefficient of friction signal, which is caused by dividing by very low vertical forces where the force is close to zero. So for this analysis, what I did is I moved the start point forwards from the 10 Newton normal threshold point forwards by 10 milliseconds, and moved the end point that we used back 10 milliseconds to try and limit the effect of this artifact. Within the remaining time of the cup, it was then divided by 50%. The first 50% was termed the braking phase, second 50% was termed the propulsive phase, and the mean value of the coefficient of friction was used for statistical analysis. To assess movement of the foot inside the shoe, we cut windows into the lateral side of the shoe upper, which you can see here approximately at the forefoot, midfoot and rear foot. So these markers were attached directly onto the skin. We then had 4 markers on the shoe outsole. You can see them on the lateral side here. They're approximately the same location on the medial side. So this video is from Qualisys, and it's a superior view. So what we're now we're looking down on top of the foot at the landing phase of a 180-degree turn. You can see the markers that were placed on the foot are in blue. So these were used to create a segment of the foot, the shoe segment, and then the colored markers, those were on the skin of the foot. So if we look at a schematic of this, I created an origin of the markers which were on the foot, which was at the midpoint between the posterior markers on the shoe. We then had our 3 markers which were on the foot. If we zoom in a little bit on this, we now have key points, and it's the distance from the shoe sole origin to the individual foot markers. And this was calculated as a 2D distance at the start of when the foot was flat on the floor during these change of direction tasks. Then what happens? These markers moved on the foot relative to the shoe sole. And then we calculated the maximum 2D distance the markers moved during the foot flat period. In-shoe sliding is then determined by subtracting the initial distance of each foot marker relative to the shoe sole origin at the start of the foot flat period, the FD1, from the maximum distance it increased to. If we plot a graph, this is to indicate what this looks like. So I've normalized this so the initial distance between the shoe sole origin and the foot markers is now starting at 0. And you can see that the individual markers move relative to the shoe sole origin. The maximum distances for each marker are shown here. So the sliding variable I report is the magnitude in difference from the sliding distance at point 0 here to the maximum. Okay, so we assess change of direction performance using a slalom course. 11 of the original 15 players did this. It involved a 26-meter course. There are 10 change of directions and 1 turn at the end. So participants start behind the timing gates, run as fast as they can. When they get to the end, they turn around and come back through the poles. If they hit a pole and it fell over, it was disregarded and the trial was repeated. This setup has been used in a previous study that has differentiated differences in footwear traction. We followed the same procedure in that participants did 3 maximal effort trials in each insole condition. There was a mandatory 3-minute rest in between trials to avoid fatigue. Now I'm going to talk you through the results. For the coefficient of friction, we found differences in the 180-degree turn task only. The thick black line here represents the mean results across participants, and the individual grey lines are each participant. We have the braking phase on the left and the propulsive phase on the right. And you can see that the training insole with more in-shoe friction increased the coefficient of friction across both these phases. And it was, the p-values suggest, as you can see, that this occurred for the majority of participants except one here. And I think there was about 3 people that did the other way around, but generally this was the case across participants. For the in-shoe sliding, we found differences in the 180-degree turn task during the braking phase. Okay, so you can see that we found that the training insole reduced sliding compared to the standard insole, and this was found to be significant at the forefoot and the midfoot. The average reduction across participants was 4 millimeters and 3 millimeters, so quite small. But if you remember, the cameras were calibrated such that the error was a maximum of 0.3 millimeters. So this seems to be a meaningful result. What about performance though? Did it work? In the slalom course, every single participant ran faster in the training insole. The average reduction across participants was 4.9%, and that was a difference of about 0.8 seconds. So good, it did what we expected. So the key message from this first study is that the insole with increased friction enhanced change of direction performance by 4.9%. We related this to biomechanical differences that we found in the 180-degree turn, specifically the increased coefficient of friction and also the reduced in-shoe sliding at the midfoot and forefoot during the braking phase of this sharper turn. I now want to bring to your attention a couple of limitations with this study. Firstly, the test shoe that we used was a prototype aimed to limit the support of the foot on the insole. So we wanted to maximize the effects of the in-shoe friction to see if the insole had any effect. However, players don't wear shoes like this. They wear regular footwear, athletic shoes that does have other support features. Secondly, the in-shoe sliding calculation does not account for soft tissue motion, and in particular, foot spreading. So if you imagine when you land your foot on the ground, it gets a little bit wider, okay? And that's going to be an artifact in the data. So moving on to future studies, I wanted to overcome some of these limitations. I love this picture. Another important aspect to address with this work is that most previous studies have predominantly assessed male participants. Some have included males and females. Cedric Morio has looked at a few studies just on females. But at the time when I was developing the next study, there'd been no comparison between the effect of friction provided by footwear between males and females. And this is despite it being reported that females have a narrower foot shape. So it begs the question if would females have additional benefits of increased in-shoe friction? So for the next study, if you remember that table I showed you at the beginning, to my knowledge, there had been 0 studies that had looked at the effect of friction in socks. And this is despite these days, and since about 2013-ish, 2014, players have started to wear performance socks called grip socks. They're typically characterized with having rubber material on the outside of the sock and sometimes on the inside. And companies suggest that they reduce in-shoe slipping and enhance agility performance. So taking this into account, the aim of the next study was to assess if grip socks reduce in-shoe foot motion and improved change of direction, in team sports players. The secondary aim was to compare the response between males and females. We tested 2 different sock conditions, a standard athletic sock and a mid-range grip sock. It was about £15, so just over $20, I think. It had rubber nodules on the outside and on the inside, so in direct contact with the skin. We felt it was really important to test it in a regular sports shoe as well, so we selected an indoor soccer shoe. Mechanical tests determined that the grip sock increased the static coefficient of friction by nearly double. To determine this, we used a rig that was similar to the previous study. I'd move institutes though, so that's why it looks a little bit different. The mass was 2.5 kilos. It was loaded on top of, here, a sample of the grip sock. Underneath that was the insole that was inside the shoe. So this was pulled at a set speed, and the peak force just before the sled started to move was used to calculate the static coefficient of friction. This image is kind of like a salami slice of, or a close-up of the sock on top of the insole. And you can see that the grip sock had these rubber nodules, which were polymer components that were protruding. So we believe that once the mass was applied, this would have increased enveloping at this interface, so it would have required much more force, or there would have been more resistance by the sock, hence the much larger increase in the coefficient of friction. For the protocol, biomechanics, we tested 20 recreational team sports players. This included 10 males and 10 females. They completed the exact same 180-degree turn, which I discussed with you earlier. With this study, we used a 45-degree side cut, given that the 20-degree side cut in the last study had no effect. Both were performed with maximum effort. From the change of direction step on the force plate of these maneuvers, we again calculated the coefficient of friction using the exact same technique. So it was the average during the braking and the propulsive phase that was used for statistical analysis. To calculate in-shoe sliding, we had markers on very similar locations to last time. So 3 on the foot, cut through holes in the upper, approximately the forefoot, the midfoot, and the rear foot. And we had 4 markers on the shoe outsole. And if you remember from last time, based on the markers on the shoe, we created a segment, and the origin of that segment is the midpoint between the 2 posterior shoe markers. Then we were able to calculate this time the 3-dimensional distance between the shoe sole origin and the individual foot markers. We calculated the 3D distance because this time, instead of just looking when the foot was flat on the floor, we matched the time periods. So we were looking at the same braking and propulsive phase as we calculated the coefficient of friction. To calculate in-shoe sliding, we calculated the maximum distance between each foot marker and the origin. And we also calculated the minimum distance and the subtracted one from the other, and this gave us our sliding variable. Here is an example from the sliding that occurred in the forefoot. And this shows you that for a few participants, we actually got this negative sliding value. Okay, I hadn't seen this happen previously, but my understanding of what it means is that if this is your shoe and this is your foot moving your right foot. Once it has slid and moved during the braking phase, during the propulsive phase, it slides back to the original position and then moves in the other direction. So the distance will get smaller. The calculation for in-shoe sliding is the maximum that occurs. So the maximum distance minus the minimum. As I mentioned to you before, one of the limitations with this method is we don't account for how much the foot spreads out. So as a first step to look into this, I thought it was important to at least calculate how much this occurred. To do this, we had an additional 3 markers attached on the foot on the medial side of the shoe. So then, as this schematic shows you, we had 6 markers in this study attached to the foot, and we calculated the distance between the markers on the forefoot, the midfoot, and the rear foot. And to calculate spreading, we subtracted the minimum distance from the maximum distance during each cutting maneuver. To assess performance of the grip socks compared to the standard sock, we did the same slalom course. All participants completed this. Okay, so now I'm going to talk you through the results of this study. We did not find any difference in the coefficient of friction. We did see some differences in the in-shoe sliding, particularly for the braking phase of the 180-degree turn. Again, I've plotted the average across participants as the thick black line and the individuals as these thin grey lines. And you can see across foot regions, the grip sock reduced the amount of in-shoe sliding. The absolute values were smaller than the 3 or 4 millimeters I reported in the last study. However, this does still seem to be quite some difference. This is the same curves, but now I've plotted the mean results for the males in black and the individual males in grey, and the average across females in green, the thick green line, and the individual females are the thinner green lines. And what you can see is for the 180-degree turn in the braking phase, females had less in-shoe sliding. This was found to be significantly reduced at the midfoot and at the rear foot region only. These next set of graphs show how much the foot spread out. So not sliding, how much the foot spread out. We can see again that the main difference is not between the socks, but actually between males and females. And again, at the midfoot and the rear foot, you can see that there is a reduction across sock conditions for the amount the foot spreads out in the females. We did find one sock effect at the rear foot. You can see here, both for males and females, there's a reduced amount of foot spreading here at the rear foot location. But an important question for any sports players is, do they make you change direction faster? The answer is yes. It doesn't matter if you're a male or female. The average across participants was a 2.9% performance in the time of the slalom course. And there was 1 or 2 participants you can see that it didn't really work for, this individual here, this male, this female, but generally speaking, it did work across most of the other 17 participants, and the p-value was 0.001. So the key points from this second study is that grip socks increased change of direction performance by 2.9% whilst wearing a regular commercial indoor soccer shoe. The mechanism could be reduced in shoe sliding. However, I want to point out we can't distinguish from this study the difference between sliding and spreading. There's still a lot of artifacts contained in the sliding results from spreading. Importantly, the results suggest that both male and female sports players benefit similarly from wearing grip socks. Okay, so we go back to the table I showed you from at the beginning now. One of the first aim of today was to try and fill the void a little bit in studies that have assessed friction between the foot-shoe interface. So now there's a few more studies here. Still though, we lag behind studies that have looked at the shoe surface interface. Since I published the study on grip socks, this year there's been 2 other studies in this area as well. The second thing I wanted to talk to you today about was how much performance gain can there be from the different footwear features in terms of times for changing direction. So what I did a review of previous studies that report times for change of direction maneuvers, and I calculated the performance difference. That's plotted on the y-axis here, and on the x-axis I have different references that have looked at cleats, outsoles, and my 2 studies here on the insole and sock. I just want to point out before discussing these results that the one study on the upper here isn't a difference in change of direction performance time. I couldn't actually find a study that had done that, so I looked at differences in contact time to assess the percentage change. Looking at this graph though, what you can see is that it appears in some occasions cleats and outsoles can have a massive difference in change of direction performance. This seems to be much greater than work that has looked at stability, keeping the foot on top of the insole platform. However, looking a little deeper into these studies, reference number 1 by Sturzing et al. In 2009, this one looked at the effect of a regular sports shoe with cleats or studs versus the same shoe where he took the cleats off. This is not really realistic to a sports situation. You're not going to do that. You want to keep your traction. The second study, which showed a massive performance improvement here by 30% by Worobits and Wanup in 2015. Here, they wanted to have a shoe with differences in the mechanical coefficient of friction and how this assessed performance. So to reduce this, what they did is they put a athletic cloth over the forefoot. But again, this is not realistic to what a sports player would do. They're not going to do that. So if we remove the unrealistic results from actual performance gains that we might see in a more realistic situation and zoom in on the other ones, this is what we have left. Please note I removed my result from the insole study as well, because I tested a shoe that was not realistic to a sports situation. It was very flexible. But if we now look at these results, what I thought was really interesting is now that cleats and outsoles seem to have a very similar performance benefit to your change of direction as to those components that help keep the foot on top of the insole platform. I thought this was surprising. I was expecting there to be bigger enhancements in those that looked at the interface between the shoe and surface. Okay, so this is my last slide of today, and I just wanted to point out something else that I noticed based on recent work, is that although it's been reported that the male and female foot shape may differ, there's been some recent evidence to suggest that they do not require different shoe friction amounts to benefit their change of direction performance. And with that, I want to thank my other authors and collaborators who helped me with this work, and thank you for listening. If you have any questions, I'll answer the best I can.
Questions? Out of curiosity, what was the material or what was the performance insole made out of, and how does it differ from more the traditional insole? What was the material of it?
That's a good question that I can't answer. It was a prototype provided by New Balance, and they were quite protective over what it was, and we didn't do anything else than assess the friction of that. So I don't know.
Was it like a general foot insole, or was it like molded for each participant's foot? And does like that impact your coefficient of friction?
Good question. It was the same. It wasn't based on a particular foot shape. It was just a set insole size for the shoe. I don't think, let's say someone wore a size US 9 and their foot was slightly smaller, it should have an effect because friction is independent of the surface area. So I think it should be the same, yeah. But
I might have missed it, but from your diagram, it looked like you had timing lights for the in-lab testing. So did you look at that performance? And if so, what was the result? And how did that correlated directly to biomechanical results?
yeah, good question. We did record the times. I didn't report them today. For the side cut maneuvers, there was no difference. And for the grip sock study, there was also no difference. For the first study on the insole, there was a difference between the 180-degree turn. They did it a bit faster in the insole that had more friction. So I guess the message, or what I was thinking about regarding this, is that in the grip socks, they were able to do the slalom course much faster. Well, 2.9% faster, but in the individual change of direction task, it had no effect. So our understanding is that maybe players can adapt to one change of direction maneuver and keep their speed the same. But when you have 10 changes of direction, one sharp turn, the grip sock then has a benefit. Yeah.
I'm glad that you removed the results from Warbits and Wena. I would not believe anything. My serious question is I think he said that the females had less sliding than the males in the second study. So do you know why that is? The difference is the speed. So what's your understanding of why they illustrate those differences?
Well, good question. Females also had less spreading. And although males tend to have bigger feet. So what I think is that because males have much bigger feet, they spread out much more. And this is probably an artifact in the sliding data and is relating to, I don't think that it was that the male foot was necessarily sliding more, but they had a bigger foot. They also applied, because they were heavier, they had larger mass, they more impulse on landing, so potentially more spreading due to that reason as well.
It couldn't be the sliding effect because of the added inertia?
We can't differentiate between sliding and spreading, so I'm not sure.
Yeah. I just feel like you'd probably be able to pick up more accurately that sliding motion than you would that spreading motion. But I have no idea how much of that spreading motion. Why do they have grips on the back of the sock? What's that all about?
You have to ask the manufacturers. I don't know why. There's no grips on the backs of the sock, so it's only on the plantar surface. It's just the design of that sock.
I see. Okay. So it's cosmetic.
Yes. Yeah. So we couldn't blind the participants in that study to the socks, because we could have wrapped something around the grip sock, but as soon as they put the grip sock on, they could feel it straight away. So they knew they were in a different sock. They knew it was a grip sock.
Yeah. And my last question, I was just curious how you're able to control for the laces.
Good question. So we asked participants to put on the shoe and tie it to their preferred amount of tightness. Then with a pen through the top eyelet, we made a mark on the lace. It was white. So then when they changed sock or insole condition, we were able to pull the lace through to the same amount with the mark to just through the top eyelet. Yeah.
Thanks.
So I was wondering, with like you have the foot spreading stuff and the slipping, did you think of taking like the mean the distance within the center of the spread to look how that changed relative to the center of the shoe?
You mean take the spreading result away from, take the sliding away from the spreading, or?
Or take like an average of what the spread was,
Mhm.
because you have to, before the foot spread, you kind of know where the center point is between your two markers,
Mhm.
and take that relative to the center of the shoe. And then your foot spreads, you kind of take that as the center point of where that is. Take the two.
I think what you're talking about is halving the foot spreading, because if you
Figure out where the center of the foot actually is after it's spread relative to the center point of the shoe.
we did try and think about methods to do this, but without getting into too many of the details, I couldn't see a way to do it, because sometimes there was a double negative in the results. I can't remember off the top of my head now why. But intuitively, the foot spreading, if the foot only spreads and it doesn't slide, the foot spreading result should be double the foot sliding, because for the foot sliding, we're just looking at motion relative to one point moving mostly laterally, but not always. Whereas foot spreading, we're just looking at the distance the foot spreads out. So I can't see a way how to do that accurately, though. With
Is this what's spreading on either side of the foot? Because that would assume that it's like if you're
Yeah.
hitting your foot at an angle, that's spreading on each other from both sides of the foot. So then maybe it would work just.
yeah, that's a good point. Yeah.
Kind of take the medial marker of the shoe, the medial marker of the foot, and get their relationship to each other.
And then then you could calculate medial sliding.
Figure out if it would help in medial and lateral to get both points relative to that origin point.
Yes. Yeah. Maybe we can have a chat about how you would do that, because this was just my best guess as a first step. But yeah, there'll be other ways. But I do think as well the medial foot might stick a little bit better, and the foot might spread more laterally. I don't know. Yeah.
Did you look at any relationship between the magnitude of foot sliding and decrease in performance? So like for a person, looking at a single participant, if they had a trial and they had a large amount of foot sliding, they have a reduction in performance.
It's a good question. I didn't look into it specifically, but I think that would be quite hard to do, because people who had more foot sliding also had more foot spreading. Typically, difference in foot volume maybe. But no, I didn't do any sort of correlation with performance based on the amount of sliding. I think it would be interesting to know, because certainly some individuals had no difference in sliding between the two socks. So they somehow managed to keep their foot still. I don't know if it was difference in foot shape or technique. If that had then no difference on their performance, I don't know. Yeah, it's a good point. Yeah.
Just between your first set of studies here and the second, I noticed that the distances went from 2D to 3D. And I was wondering if part of that was, did you capture any rotation of the foot relative to the shoe? is this influencing your 2D results?
I don't think that will influence the 2D results because we only assessed when the foot was flat on the ground. Okay. So the reason then to go to 3D is because we presumed that there would be some sliding before when the foot was flat. So we changed it to a 3D distance. If that answers your question, I'm not sure.
What was the friction coefficient?
For it was around 0.6 for the 180-degree turn.
Do you know what the friction coefficients are in the tennis players on the artificial surface that slide now meters?
I don't know, but I imagine if you're talking about elite players, they probably are able to increase the coefficient of friction more. I've not looked at tennis players before, but
They slide much more. It's unbelievable. I mean, when I did my studies on tennis, they didn't slide at all on these artificial surfaces. And now they slide meters.
even on the hard courts, I think the best players slide on the hard courts, which is
Yeah.
shocking.
I mean,
Yeah, yeah,
which is similar to what you have.
yeah. I think it's
Will you have less? Would each players have less or more?
I'm pretty sure the players I assessed, the participants were recreational. So yeah, the ability was probably to change direction was lower than these elite tennis players who were sliding. So my guess is that the friction coefficient I report will be lower than elite tennis players that are able to slide. Off the top of my head, I don't know what those values are for studies that have looked at tennis players.
Friction coefficient.
Sorry.
Which ones are those? Your subject or the tennis players?
My subjects. Yeah. I would check, I think, what's her name? There was a group in Man Met, Chelsea Starbuck did some studies on tennis players and reported the friction coefficient values. I think my results are not too far out of line. I can't quote her findings, but again, I think you're talking about elite players sliding. I don't know, I've not watched much recreational tennis to know if they also do that, but my feeling is the elite players are able to.
Your test subject didn't slide.
We didn't monitor foot sliding. Sometimes they did slide a little bit, but it wasn't meters. It was a tiny slip. Yeah. Well, we could calculate that though, because we had markers on the foot. So we can calculate from initial contact where they moved to for sure.
But then you would have static coefficient.
Correct. Yeah. Which is lower than the static coefficient of friction. Yeah.
Sure. Okay. Is there any, like, should you limit all foot sliding in the, or the foot sliding between the shoe? Is there some benefit to having some of this?
From a performance point of view, there's no benefit, because if you're sliding, it's taking longer to stop. And when it's taking longer to stop, it's taking longer to change direction. If you increase the friction too much, then maybe you're more likely to get a blister if you increase the friction too much. So studies on outsole traction talk about there being sort of an optimal amount once the coefficient of friction values go beyond sort of 0.8. There's no further benefits to performance. In terms of in-shoe friction, I don't know if there's that relationship. I don't know if we have a more grippy grip sock, if it still helps, if there's further performance gains or not. We did do some subjective testing as well on the grip socks. And interestingly, all players found them more comfortable than the athletic socks. So they actually quite like the feeling of less slipping. Maybe if it's just a complete rubber material on their foot, it probably has other issues with sweat. Maybe it's uncomfortable, maybe you get blisters and then it's not so fun. But for performance, no, I can't think of a limitation of you want your foot and shoe to be one. It's better for ball control as well in soccer.
Did you cut holes in the grip socks then to get the? Okay, interesting. Do you think that jeopardizes the integrity of the sock at all?
I don't think it jeopardizes the integrity of the sock. No, I think it might. I think it's more likely because the sock is quite a loose material. It's not rigid, but certainly cutting holes in the shoe might have affected the structural integrity of the shoe. So, you know, my method uses motion capture. There's no way around it. If there was a way, if I had a biplane fluoroscopy machine and could just look at the motion inside the shoe, maybe the shoe is able, maybe it has more structural support. But my Nottingham Trent University doesn't have one. No.
So you've shown some pretty compelling results on performance with respect to the shoe sliding or the foot sliding. And I'm not sure if any of the shoe or sock companies care as much about injury as they do performance, but has any of the studies looked at the effect of this maybe reduced sliding on the upstream like joint mechanics? Like, is it affecting the knee mechanics? Is it have any effect on injury risk during these cutting tasks?
In shoe friction, no, I don't think we've looked at that. Cleats and outsoles, yeah, some studies have looked at that, and I think in the end there was no evidence for it. But I don't know if you remember bladed soccer shoes. So instead of having rounded studs, they were kind of a more rectangular shape. It was believed these might increase the risk of fixation, and it's the same if you have an outsole with too much rotational friction, it might fixate the foot on the ground, and then that can lead to serious injuries, and it probably would change the mechanics. Yeah. So there have been a few studies that talk about injury as well, but I agree most companies don't talk about injury risk. They're just interested in the performance benefit. It's easier to quantify and easier to sell products.
I might have missed it at the beginning. Just wondered about some of the methodology. Did you test for reliability, and how many times did people repeat the test, and what was the inter-test reliability that you found?
That's a good question, and that was something I was thinking that I need to do a study on. But they did the change of direction tasks 5 times. There's been other studies that have found that you need to do a change of direction task 3 times is reliable enough. But we didn't do any retest reliability. I think we had one person come back for the insole study, and we found similar results in the coefficient of friction. In terms of the slalom course, the Sturzing study set this up, and they have found it to be a reliable method. Yeah.
And they did it once.
They did this one 3 times with maximal effort. They did we set it up so they did 1 submax test in their own shoe first, and then they did 2 submaximal tests in each insole or sock condition. And then this was before they did 3 maximal effort ones in each sock or insole condition. It was swapped every time, and there was the
order there was randomized.
Yeah. Yeah, so every time they'd swap. So it wasn't that they'd do 3 in one insole and then the other, because there might be fatigue, even though there's a 3-minute rest to try and avoid that between trials.
And so when I did this 3 times under the same condition, what was the time difference from the best to the worst trial compared to the difference that you found from the one condition to the other condition?
Between trials? I need to check my results, but they were remarkably smaller. Yeah. I And we took the mean as well, so it wasn't like we took the
So
max.
you took the mean of
Yeah,
the
we
street.
took the mean max. So yeah, there was, I can't comment on the exact difference in between trials, but it was a lot smaller than the difference between the sock or the insole, for sure.
And the other thing that I was wondering, when you showed the, going in and then 180 degrees back, did you ask people to place the foot in a certain position on the platform?
Good question. No, we wanted to see what happened naturally when they changed direction.
And did you find that with the different conditions, people adopted a different foot placement, which might affect on how much they slip sideways?
Good question. There were most players just planted their foot for the 180-degree trial or task, sort of parallel to the force plate. So they'd come in, they'd plant their foot sort of sideways on and run back. We had a netballer and a hockey, no, she was a soccer player, and we had a netball player. I know it did have a different technique where they, during the 180-degree task, they kind of already turned by the time they did the task. I didn't know. So did you see what I did?
Yeah, no,
Yeah.
I'm
Yeah.
just trying to.
So, but I did look at those two participants, and I didn't actually see that there was a difference in in-shoe sliding despite their different strategy.
And so the command that you gave them was just run as hard as you can to the platform.
Plant your dominant foot and run back.
Run back.
Yeah.
Like turn as quickly as you can.
Yeah. Yeah, and it didn't really give any demonstration, because if they would have watched me, then maybe they copy what I do or something.
Did you find that people did that quite stereotypically, or that different people had different techniques aside from the foot placement?
Not that I remember, no, because they were all recreational team sports players who were kind of used to doing sort of changes of direction. I mean, if we did a biomechanical analysis, I'm sure we would find that there were some different strategies, but observing what they did, I didn't notice that some were sort of doing a different leg placement upon landing or anything particular, apart from those two that I mentioned for the 180-degree turn task, where I'd noted that instead of just planting their foot approximately parallel, they were nearly changing direction before they planted their foot.
Coming back to the sliding question that was asked, I mean, if you ask me, run to a point and turn around as quickly as you can, and then obviously I would try to avoid sliding. But in tennis, never played tennis, but if I slide a little bit, who cares? Because I have, I don't know, half a second, 2 seconds, I don't know. You have lots of time.
Mm-hmm.
Okay? So I was wondering if you had asked the people to slide, to run on the platform and slide as far as they can, do you think they would have been able to slide? Because it seems to be a different technique that you would use if you asked them to slide, or if you asked them to return as quickly as they
I think it's a sport specific thing. I think if you've got tennis players in who are used to that, I think they can. But netballers are not used to that at all. So they're used to like landing and literally having to stop. They don't slide. So I think some, depending on the sport and the individual, some would be able to slide, is my feeling. Others would need some more practice to be able to do that. Yeah.
But if you have put a tennis player, an elite tennis player, into that situation, you think they would have been able to slide in your setup?
Probably yes, but they wouldn't have been in a tennis shoe.
Just to comment on that, having been a tennis player, not all tennis players would be able to slide. So more tennis players are comfortable sliding when they're clay court players compared to hard court players. Clay and grass is more common for sliding, and so someone that would be more confident and familiar with that probably also slides quite a bit on hard court. But someone like Federer, who's a dominantly hard court player, slides less than someone like Rafa.
Even on the same court?
Correct.
Even on a hard court?
Yes.
We need to get some tennis players in.
Like the Kirby socks, honestly, like
long distance running, like in terms of being on roads that have like when it's kind of tilted to the side. Like, I find for myself that like I slip sideways with my shoes on.
Yes, potentially. I was thinking as well as another application is hiking, especially here down down the Rockies, down a mountain. I personally have had sore toes when my foot has slipped forward. And I guess this is more an extreme example of the running. So yeah, in trail running, maybe they might be useful. One thing to consider is sweat. So you sweat a lot more and you're in those sort of you typically run longer than you play football, or at least elite runners do. So if it becomes uncomfortable over a longer period and the friction increases and you get a blister, is something to be aware of. But I don't see otherwise why it would not help with that.
But a question, so right now with the conversations with tennis and then this study, I see two parts of sliding. So your study looks specifically at in-shoe sliding. And then when we talk about tennis or other sports, it's like on the shoe and ground sliding. So are you familiar with whether there's an optimal amount of sliding in shoe and ground, and then does that relate to in-shoe sliding? Or do you want to like completely stop in-shoe sliding, but you need some sliding with shoe and ground interaction?
Good question. So from what I mentioned earlier, I think in-shoe sliding is bad. It makes you feel unstable. Sliding between the shoe and the ground, you probably know a little more being an ex-tennis player than me, but I think, yeah, potentially there might, in some scenarios for the sport, it might be beneficial to slide, but in other scenarios, you know, when you want to, you want to, you go and there's a defender ahead of you and you want to go left, you want to do that as quickly as possible. You don't want any sliding particularly, that's just going to slow you down. You probably, in that scenario, just want to change direction as fast as possible, no sliding. So I think tennis is maybe a sport-specific sliding thing. I'm trying to think of other sports where it's beneficial to performance. Curling.
Like trail run. If you look at like elite downhill trail runners, a lot of
They
them
slide.
engage into some sort of sliding motion. And
Yeah.
that just means that they take fewer steps.
That's a good point, yeah.
Another really different sport where relative motion between foot and footwear is important is alpine skiing. And I haven't heard of anyone using grip socks in alpine skiing. It's quite common to wear no socks and go for all sorts of other quite extreme interventions to have your boots A, as stiff as possible, and B, have as minimal amount of relative movement between foot and boot. And so I'm wondering, you know, is that a potential avenue for alpine skiing? But at the same time, taking the converse, like, is it so much increasing the friction inside the shoe or just reducing the amount of space that the foot can move within a shoe selection?
You might need to repeat what your question is. So you're asking if alpine skiers might benefit from grip socks, or?
But yeah, that's part of it. So it seems to me that there's a couple of strategies that you could employ to reduce the amount of relative movement between footwear and foot. One is to increase the friction inside of the footwear. The other one is just to reduce as much space as possible inside the footwear.
Yep.
And then use a stiff material that
Yep.
doesn't move,
Mhm.
so it can't stretch, etc. And I guess I'm wondering if what's after doing this type of work on the relative importance of one versus the other, or it would seem that alpine takes, or skiing takes the one extreme, remove as much space as possible, and maybe football and other things are going towards increasing friction.
Yeah, I think, I don't know with alpine skiing, but I imagine the horizontal forces might be less. So the coefficient of friction might be less. So it might be that they don't need the sock for comfort, in which case, yeah, just reducing the space might be better, is my initial thought. Whereas in team sports where there's very high horizontal forces, you might require a sock, just because otherwise it might be very, in some cases, I imagine it's very uncomfortable if you don't have that layer in between might hurt. You might get some rubbing is what I would think, just because you have higher horizontal forces.
Horizontal force is quite high in skiing, but.
Okay, I'm not a
try to put
skier, sorry.
halfway up there, big.
Yeah.
Well, let's thank Charlotte again.